In this lecture, we will talk about what is a belt pulley arrangement. We will see how friction plays an important role in transmitting power in a belt pulley arrangement. In this process, we will try to derive the relationship between the tight end and the loose end in a belt pulley arrangement in the belts, which causes the power transmission. So, a belt pulley arrangement is used for transmitting power between two parallel shafts. When a small sketch is given here, one is called as a driven, the other one is a driver, and the other one is a driven. This is a driver, this is R. Okay, it looks like N. This is a driver, and the other one is a driven, which the driver could be a motor, the driven could be the system which is designated for a particular object. Usually, flat belts are made out of canvas material, and the flat belts or V belts, there is a difference in tension between the tight end and the loose end. One side of the belt is tight while the other end is in loose when it is in operation. I have shown a simple sketch wherein one end is tight, the tight end is on the direction in which the power is transmitted, and the other end is loose, which is coming in. So if I call the tension at the tight end is T1 and T2 as the tension at the loose end, theta is called as the angle of lap. The angle of lap is the angle which the belt makes on the pulley. This is for a flat belt in general. For a V belt, the operation is all same except for the geometry of the belt. V belt has a trapezoidal cross section, and they are capable of transmitting more power than a flat belt. So we need to address this issue also. Why V belts can transmit more power than. To understand this, to answer this question, we need to study the geometry of the V belt. So let us look at the geometry of the V belt. A flat belt is made out of, as I said, it is made out of canvas and it's flat, rectangular in cross section, while a V belt has a trapezoidal cross section. There is in a rubber matrix you have steel cords which are used for transmitting power. This is the construction. While if you look at it, the trapezoidal, the included angle for the trapezoidal, we'll call it as 2 alpha, and the belt sits like this in the pulley as shown in figure. There is a small gap between the belt and pulley. The contact is on the sides, on this side and on this side. So you will have friction on both these sides. It is subjected to frictional force, and this frictional force brings in the power transmission. While in case of a normal flat belt, the belt sits over the pulley like this. If this is the pulley cross section, the belt sits over it like this on a flat. This is the belt and this is the. So here you will have a normal reaction which is going to be up R, but in case of a flat V belt, the normal reactions is on the normal to the surface of contact. So let us talk about what is the normal reaction in case of a flat belt and a V belt. I will draw the sketch of a flat belt here, and this is going to be the normal reaction for a flat belt, and this is for a, which I have already drawn to save some time. So the normal reactions are R1 and R2, which is pressing the surface, or the surface in turn presses it on the sides of the belt. Here you will have the normal reaction R1 and R2. So resolving the forces, R here is going to be equal to R1, the normal reaction to the surface is going to be R by 2 sin alpha, or R the normal reaction to the surface is going to be 2R1 sin alpha. Now, having seen this, we will talk about the how friction plays in a belt pulley arrangement. This part of the derivation is for both flat or a V belt. So let us take the cross section. First, let us look into a belt pulley arrangement. This is R, and the belt moves like this. This is the thickness of the belt which goes down like this. This is the angle of lap. As defined earlier, theta is the angle of lap. Let us say the belt is turning in this direction with an angular velocity omega, and this is your tight end. So T plus dt, and this is it has to be designated as T2, and this is T1. I am interested in finding out what is the relationship between T1 and T2, irrespective of whether it is a flat belt or a V belt. So to do it, we will take a small elemental belt area which makes an angle 2d theta. Now let me draw the free body diagram for the small elemental area of the belt, which makes an angle d theta, and we will try to examine what are the various forces in it. So you will have a tension. If we assume that the belt is moving in the clockwise direction, on the right hand side you will have T plus delta T, and to the left hand side T. This difference in tension is going to transmit power, and we have to find out what is this difference in tension. And you will have a normal reaction. Since the belt is pressing the ground, you will have a normal reaction R. In case of V belt, you will have a normal reaction which is the belt is not pressing the ground, but instead the belt is pressing on the sides as we have seen it earlier. So resolving it, the normal would be equal to 2 R1 sin alpha, where R1 is the normal at the sides at the trapezoidal sides of the trapezoid. Okay. Now we will look into the various force. The other force which is going to come into action is the friction force, which is going to be mu r. So for a flat belt, you will have, irrespective of whether it is a flat belt or a V belt, you will have mu r acting like this, and you will have a T cos d theta by 2 if I were to resolve it in the horizontal direction, and on the right hand side you will have T plus dt cos d theta by 2. Equating it, we get this equation, which is going to be T cos d theta by 2 plus mu r will be equal to T plus delta T cos d theta by 2. And along the vertical direction, the sine components of the tension, T sin d theta plus T plus dt sin d theta will be equal to the normal reaction. We will make a small approximation which says that for small angles, sin theta is theta and cos theta is 1. So using that, if I simplify, I get mu, substituting that in the equation, we get mu r is equal to dt, and further simplifying, taking into consideration dt into d theta is too small, neglecting it, you get r is equal to T d theta. I will call this as B and the previous equation as A. Substituting for the value of r in B, in A, you get mu T d theta is equal to dt. This is for a flat belt. For a V belt, we have already shown that r, though the belt does not press on the base, but it presses on the lateral sides, and because of that you have a normal reaction R1, and R1, if R is the normal to the surface, R is equal to 2R sin alpha, and substituting that, and there is friction on both the sides of the trapezoidal. So you will have, this is for a V belt. T cos d theta by 2 plus 2 times mu R1 is going to be equal to T plus dt into cos d theta. Simplifying that, I will get 2 mu R1 as dt, and substituting the value of R1, you get mu by sin alpha into R is equal to dt. I will call this mu by sin alpha as mu dashed. If I say mu by sin alpha is equal to mu effective or mu dashed, here I have shown it as mu dashed. The equations of your flat pulley and the V belt looks alike. Further simplifying, integrating it, taking between the limits T1 to T2 and integrating it as shown below, you will get a ln T, which is equal to mu theta, and substituting the limits I will get T1 by T2 is equal to e power 1 minute, it is T2 by T1, I am sorry, T2 by T1, that is the tension end to the slag end, is e power mu theta, e power minus mu theta 2, and this is 1. Since mu dashed, which is going to be mu by sin alpha, both mu and sin alpha are less than 1, decimals, 2 decimals, division of a decimal by another decimal will give you a whole number which is greater than 1. The power transmitted in a V belt pulley is going to be T1 by T2 e power minus mu dash of theta is going to be always going to be greater than e power mu theta, e power minus mu theta. Hence, V belts can transmit more power. Thank you.